Let's continue our consideration. We are proving conformality of angles under inversion, under the transformation of inversion. So let's proceed as we were going to. Q minus z over p minus z is a number for which we are going to find the argument. The ratio of the imaginary to real part of this number will be the tangent of the argument of this number. So it will be our original angle alpha. I will act as usually. I multiply and divide by the conjugate to get rid of the complex of the imaginary parts in the denominator. So I will write it as q minus z divided by p minus z and p conjugate minus z conjugate, and here I multiply also by p conjugate minus z conjugate, and this will give us in the numerator, in the denominator, a real positive number. So it will be now q minus z rho e to the power I theta minus z, q minus z, q is r e to the power I phi minus rho e to the power I theta. This is q minus z. Now p conjugate minus z conjugate will be r e to the power negative I phi, because it's conjugate, minus rho e to the power negative I theta, and divided by p minus z modulus squared. And for the future calculations I will denote p minus z modulus squared. It will be some number d. D is real number and d is a positive number, right? So d is a real positive number. We will just write it as d. I think I have to erase things, and then I don't need this picture anymore, but we will need to do a lot of calculations, so we need some room. Now it equals, I think we'll just have to multiply through. R e to the power I phi e to the power negative I phi will cancel, so it will be just r. Now r e to the power I phi rho and e to the power negative I theta, so it will be minus r rho e to the power I phi minus theta. I think I have to write a little bit larger letters, so it will be r minus this term times this term, r rho e to the power I phi e to the power negative I theta e to the power I phi minus theta minus r rho e to the power I theta minus phi and rho e to the power I theta e to the power negative I theta, and so it will be plus rho squared, and the whole this thing is divided by d. Now, in order to extract the real part and imaginary parts, we need to rewrite these two terms in trigonometric forms. That's what we will do. So first of all I will write real part r plus rho squared, and then I will write minus r rho cosine phi minus theta. Maybe I will need a lot of room, so I will maybe instead of writing the fraction, I will write it equals 1 over d, and then I will open a huge bracket, and then I can continue writing r minus r rho cos phi minus theta minus r rho minus I, because it will be I, yeah? The part with sine, r rho sine of phi minus theta. Right? Now I will write this term minus r small rho cosine of theta minus phi, and minus r small rho sine, and there is I here of course, I before sine part, sine of theta minus phi. I think we can close the bracket with this. There is something I lost, plus rho squared, I will write it there, plus rho squared. I think that will be it. Hopefully we didn't make mistakes. Equals. Need some separation line, as it's almost so long, it's easy to make mistakes. Equals 1 over d. Now I will open this big bracket, and I will collect together real terms and then imaginary terms. r plus rho squared. Now we have this term, this cosine, they also belong to the real part. So I will write minus, factor out rho, and here will be r plus r. And cosine phi minus theta is equal to cosine theta minus phi. So I will just write cosine phi minus theta. It is the same. It is the same cosine, because cosine is an even function. For sine, it is opposite, because for sine we have sine of phi minus theta is negative sine of theta minus phi. So I will write here plus I, and here I will change to sine theta minus phi, so I will factor out rho, and this term is go with plus r minus r, and it will be sine of theta minus phi. I think we did not forget anything. If we did, it will be tragic, because it's a long calculation. Have a look. I think it's pretty much, it's pretty much the same. So I think it must be true, and this I will denote real part by one letter and imaginary part by another letter. Suppose I will denote the real part n and the imaginary part m. So it will be 1 over d, and it will be n plus I m. And as you know, tangent alpha will be m imaginary part over real part over n. So it will be in this case, this is imaginary part, rho r capital minus r small sine theta minus phi divided by this whole thing, real part, r plus rho squared minus rho r plus r cosine phi minus theta. That's our expression for tangent alpha. I hope it is seen well on the board. This is our expression for tangent alpha. Yes, it is seen quite well. And now we'll erase everything here to have room for writing, and we will get tangent beta of the angle into which alpha has been transformed as a result of the inversion. So what will be I don't have to repeat the whole this calculation. We can do it, we'll do the same, but I will just use tangent alpha expression to write tangent beta, because I can just replace these numbers with what they have become after inversion. So it will be 1 over rho 1 over r capital minus 1 over r small sine of negative theta plus phi divided by 1 over r plus 1 over rho squared minus rho r plus r cosine of minus phi plus theta equals. Now I will just multiply the numerator and the denominator by rho squared r. Yes? So I will multiply the numerator and denominator by rho squared r to get rid of the things in the denominator. So here I will have rho, here will be r small minus r capital, here will be sine of phi minus theta. What will be here? Rho squared, because multiplied by rho squared r plus r minus, and this I made a mistake, it must be what? 1 over rho 1 over r plus 1 over r, right? I'm replacing these expressions with what they have become after the inversion. Minus rho, and here will be r small, and here will be r capital, cosine of theta minus phi. Is this expression, are they different? Let's see. If I replace r minus r with r minus r, I will get minus. So I will have negative sine of phi minus theta is sine of theta minus phi. So I can just write r minus r, so I multiply it by -1, and I multiply this sign by -1, so I will get sine of theta minus phi divided by r plus rho squared, r plus rho squared minus rho r plus r and cosine theta minus phi. Cosine is an even function, so cosine of theta minus phi is the same as cosine of phi minus theta. And this is exactly tangent alpha. So tangent beta is equal to tangent alpha, and that's what we were going to show, the conformality of inversion. I think we have finished this part of the story. We discussed the inversions and their properties. What shall we do now? Now we shall consider something that will allow us to view the inversion as a one-to-one transformation. We will enrich our complex plane by adding something essential. If you remember, all transformation must be one-to-one, and under inversion, when you perform the inversion, W equals 1 over Z, and we obtain sometimes figures that contain the origin. For instance, as a result of our inversion of a straight line, we obtain a circle like this. So the origin is on this circle, but there is no origin on the straight line. What is the preimage of the origin? That's a painful question. We don't know yet. And our transformation must be one-to-one, so every point must have exactly one preimage, right? Our transformation is a bijection of the complex plane onto itself. So let's do something interesting. This interesting is called stereographic projection. Stereographic projection. Stereographic projection is an important thing that allows us to interpret complex plane, complex numbers in a very special, in geometrical sense way. So, suppose above the complex plane we have a unit circle such that the origin of this unit sphere, not a circle, but a unit sphere, and the center of this unit sphere is located at the origin of the complex plane. It will look like this. To make as good a sphere as you can. Exactly as we would like to, but still you can make a decent sphere. So this is a sphere, and this is a section of this sphere by a complex plane, and this is the center of the sphere. So let's do the following. We can imagine that this complex plane is a plane, and it's not completely transparent, so all the lines that lie beneath the plane we don't see them well, but we can imagine them, and so I will draw everything that we don't see clearly but we can imagine. I will draw in dotted lines. And this is the origin. And let's consider the axis. This is the real axis, imaginary axis, and this will be the real axis. See, according to the plan, I'm drawing things that we don't see in dotted lines, so as long as this axis goes inside, stays inside the sphere, it's in dotted lines, right? And now there is a third axis. There is a third axis that penetrates through the sphere, that pierces the sphere at the top point, and this top point we will call N. N is the north pole. The whole this sphere I will denote sigma. This sphere sigma is called the Riemann's sphere. This is of course the south pole. Now how do we establish the connection of the sphere with the complex plane? So this is imaginary Z. This is real Z. Through every point of the sphere, we can draw a straight line connecting the north pole with this point. For instance, if I look at this point P lying on the sphere, I can draw a straight line through this point. It's invisible inside the sphere, but then it becomes visible here. This will be point Z. So Z is a stereographic image of point P. And this S will be our notation so far for stereographic projection. Now, Z is a complex number, of course, it lies in the complex plane, so if I draw a line parallel to the y-axis, it doesn't have to go through the south pole, you can draw the south pole somewhere here. Just a coincidence. This will be the x-coordinate of our complex number, and I will draw the line parallel to the real axis. This will be the y-coordinate of our number, right? Z is equal x plus iy. And what about the coordinates of point P? The coordinates of point P will be, if I draw a line parallel to the line connecting Z with the origin, the line parallel to this will be the perpendicular drop from point P onto the vertical axis, and this axis, the third axis, I will write the title, right? I can erase things, write new ones. This axis I will call zeta. In your textbook it's called C-axis, but calling coordinate axis A, B and C is not a decent notation. So this axis I will denote zeta. It's not difficult to write. You write a loop like this and then something like this. It's like a praying woman, a woman is praying, sitting on her knees and praying. For the good luck of all of us. So, this is a zeta coordinate. North pole, of course, stands at zeta equal to 1 because the radius of the unit surface is 1. So this point is also 1. This point also has coordinate 1. Right? Because it will be the unit circle in complex plane. Now, what else? If I draw perpendicular here, the coordinates will be respectively, I will denote them psi and eta. In your textbook they are denoted A and B, which I don't think is decent. So the coordinates of point P are psi, eta, zeta. As one concession to your textbook, I will write here A, B, C, and I will try not to use A, B, C too much because it's not decent. So these are the coordinates of point P. How are they connected? Connection to x, y, the coordinates of the point in the complex plane. Let's see. The vector connecting O with point Z, here it will be a good idea. It will be a good idea, and we will often use it. I will raise something there on top, and I will repeat this picture, maybe to a smaller scale, but I will make a flat picture of the cross section of this by this plane, cross section of the picture by this plane passing through the North Pole, through the origin and point Z. It will be much more convenient for our consideration. By the way, if you look at the pictures in your textbook, their picture is not good. In their picture, North Pole is located here, which is wrong. It cannot be. If you look at the sphere from the side, then North Pole is located here. If you look at it from above, North Pole will be seen as somewhere a little bit lower. So anyway, I will repeat this picture with a Riemann sphere. And there is a complex plane, I will write it C, and there is the zeta axis, there is North Pole with coordinates 0, 0, 1, right? It is just above the origin. This is the origin. This is the South Pole. By the way, now North Pole is seen on top of this circle because we have a flat picture. And then there is point P and point Z. So this vector OZ of our interest, if I draw perpendicular, I have to give name to this point. Why don't I call it point Q for now? And I will draw perpendicular on this axis, and this will be coordinate zeta. I will give the name zeta for it. So vectors OZ and OQ are collinear. So OZ, I will write it like this. I could just write number Z, but it will not be so explicit. Yes, OZ is equal some coefficient multiplied by OQ. What is this coefficient? The coefficient k is the coefficient of similarity of the two triangles. This triangle O N, this point is N, right? O N Z, and this triangle zeta N P. You know, instead of denoting this point zeta, because zeta is actually the coordinate, the vertical coordinate, I will put here some letter M. This will be point M with the vertical coordinate zeta. So the similarity of this triangle is pretty clear, that the side of the great triangle is to horizontal side of the smaller triangle as the vertical side of the great triangle to the vertical side of the small triangle. That's what I will write. The horizontal side is OZ modulus, so you could write modulus of number Z over this side MP. I can just say the length of MP, doesn't matter. It's a vector MP or the length of vector MP as the vertical long side is 1, it's a unit sphere, over the vertical side of the small triangle, 1 minus zeta. So OZ, the length of OZ will be 1 over 1 minus zeta multiplied by the length of MP. Since these vectors OQ and MP are parallel, this relation will also hold for vectors, yes? So OZ will be this coefficient. I can say that this will be our coefficient K, yes? 1 over 1 minus zeta will be the coefficient of proportionality between two triangles. It will be this coefficient K equals to K vector MP. This vector MP. Or now I can write it in coordinates. The vector MP. I can say vector MP will have the coordinates of point P minus coordinates of point M. This is point M, right? In our notation. So the coordinates of point P minus coordinates of point M. So it will be the coordinates of point P psi eta zeta minus the coordinates of point M 0, 0, zeta. That's the coordinates of point M, yes? It's located on the vertical axis above the origin. So it will be psi eta 0. So vector OZ, or we can just say it is number Z, which has coordinates x, y, 0. It lies in the horizontal plane, in the complex plane, equals this coefficient, which is 1 over 1 minus zeta, 1 over 1 minus zeta, multiplied by the coordinates zeta, eta, 0. So we can conclude from here the expression for the coordinates for the real and imaginary part of number z. X equals 1 over 1 minus zeta psi, y equals 1 over 1 minus zeta eta, or we can say for the number z, I will erase this part because we don't need this anymore. Number z, which is also vector of z, number z equals x plus iy, and it is equal 1 over 1 minus zeta psi plus I 1 over 1 minus zeta eta. That's a connection between, so this will be formula 1, this you can take as formula number 2, the connection between the coordinates of point P and the coordinates of complex number in the complex plane. What else is interesting before we proceed with studying the stereographic projection? Right? What else is interesting? You see, we made one-to-one correspondence between the points of the Riemann sphere, sigma, that's what we call the sphere, Riemann sphere. For every point P, we have a point Z lying, in the complex plane, right? And for any point Z, we can draw a straight line connecting this point Z with the north pole, and we will have some point P where this line intersects the Riemann sphere. So there is one-one correspondence between Z, point Z, and P. Is it really? Let's think for a second. And then ask the question. Every point on the Riemann sphere has the corresponding point to the complex plane. Or is it? What about the North Pole? This is North Pole. What about the North Pole? What is the stereographic projection? Stereographic. I'll write it like this. Stereographic image of the North Pole. That's my question. What is the stereographic image of the North Pole? Whenever I want to draw a line through North Pole, how do we get image of P? We draw a line through North Pole and P. If I draw a line through North Pole and North Pole, what will be this line? It will be lines that go like this, horizontally. In our regular notions, it will not intersect the complex plane. However, we will enrich the complex plane. We will add to the complex plane a point z equals infinity, which is the image, the stereographic image of the North Pole. That's our definition of the point called infinity. That's our definition of the point called infinity. So, if we draw another horizontal line, we will get another point at infinity? No, we need exactly one image for stereographic projection. So, all the other points, infinity is a single boundary point of the complex plane. And now we will say, let's introduce the new notation, a new complex plane, better than the previous one. new complex plane better than the previous one. Complex plane, you will call it C with bar above it. C with bar above, it's a, you can say it's a closure. By this bar, usually, if you have an open set, a set that does not contain its boundary points, when we include boundary points, we denote the same set with the bar above it. So it will be ordinary complex plane and the point at infinity, which is an important point. Yes? And it's usually called the extended complex plane. And in the future, we are going to consider all our transformations because it is convenient to consider this for inversions. We consider all our transformations in the extended complex plane. Extended complex plane. Now, when considering transformations like inversion, we will have a point that can be viewed as the preimage of the origin, because before that we did not have a point. We did not have a point that could serve as a preimage of the origin under inversions. And now we have a very good candidate for such a role. And then we consider it next time.